15 lecture of the electrostatics. In this lecture we are going to discuss about the Gauss theorem. I give a relation between the electric flux through any closed hypothetical surface we are going to take out. This hypothetical surface is known as Gaussian surface, and the charge enclosed by the surface, we are going to find out the relation between them, and state that the total flux phi through any closed surface is equal to 1 by epsilon naught times the net charge q enclosed. Remember, it enclosed by the surface, the hypothetical surface that we had taken. Explaining the Gauss theorem, let me consider that this is the some charge distribution, and we have taken the sum of the charge inside this surface. This dark gray surface is the this is the surface. Dark gray surface is nothing but the Gaussian surface, you can say, the imaginary surface that we have assumed. Gaussian surface, it might be of any shape, it depend upon the charge configuration, what the charge configuration we are taking out. And this is the dA element direction. Let me change the color. This is the dA direction, and dA, the area element that we have taken, and direction of the area element is perpendicular to the surface, and this is the E vector, and the angle between the dA vector and E is represented by the theta. We are going to discuss because the flux is, we have taken the E vector dot ds vector, and here the dot product, yes, and in the dot product, if we write E magnitude, ds magnitude, and cos theta, then theta is the angle between the E vector and the ds vector, yeah, dA vector, that I have represented in this diagram. And this these are the electric field lines coming out from the Gaussian surface area. And the flux is, then let's suppose the q enclosed, the total q enclosed, charge enclosed is capital Q. Then the flux, yeah, you can say from the Gauss theorem, you can simply say that the flux through it is q enclosed by 1 by 4 pi epsilon naught into q enclosed. Yes, this is the flux coming out from the Gaussian surface area. This is given by the charge enclosed. This is the charge enclosed in the Gaussian surface area, and this is the flux. Total flux is equal to 1 by 4 pi epsilon naught. 1 by epsilon naught sample the into q enclosed in the Gaussian surface. Okay. Shape of the Gaussian surface. For let me take first the point charge. Due to the point charge, what is the shape of the Gaussian surface? It is spherical. Okay, it is of spherical shape, but in the 2D you will see that it is a circle. Basically, in the, if you have the point charge, the Gaussian surface look like the spherical. For the point charge distribution, spherical, there is a spherical Gaussian surface. Basically, you can look at the screen, and in the diagram they have shown that there is a point charge, there is point charge in between, and this blue color is a spherical Gaussian surface due to the due to the point charge distribution. And they are also representing the dA vector direction. This is nothing but perpendicular to the surface, and E is the electric field perpendicular. Basically, it is the direction of the electric field is radially outward. We will discuss in the next classes most probably. And line charge distribution. If you have the line charge distribution, let me define the lambda, a line charge distribution parameter for it, and lambda is nothing but, most probably we'll discuss in the next lectures. But basically right now I am just telling you that Gaussian surface due to line charge distribution is of the cylindrical shape. You can see the diagram here, and simply it is showing that it is of cylindrical shape. And then if you have the uniform electric field, then you will get with the if you have the this is the uniform electric field, this is the uniform electric field direction. And if you have the uniform, then the Gaussian surface is it is the this plane, it is in the red color. This plane represent the Gaussian surface area in the uniform electric field. Thank you.